Okay, today's talk is about TLS, and some stuff that you may have heard of, and some stuff that maybe you haven't heard of, and some funky public key infrastructure stuff. Just an introduction to a bunch of stuff, but not a super deep dive into anything. What is TLS? It's a protocol used to encrypt and authenticate application layer traffic. It runs on top of TCP. It's the successor to SSL, so you might hear SSL or sometimes you might hear TLS. They're the same thing. Well, they're different in that SSL is older, and SSL is broken to the point where really nobody should be using it anymore. There's SSL version 2 and SSL version 3, and TLS has had 4 versions, 1.0, 1.1, 1.2, and 1.3. We're only going to talk about 1.2 and 1.3 because everything else is you probably shouldn't use. Where's TLS used? In a lot of places for HTTPS. That's where the padlock from your that's what the padlock on your browser indicates. OpenVPN uses TLS. It's used for Wi-Fi authentication, like at UT when you sign in with your UT ID and password. Part of that authentication protocol relies on TLS. You can actually, there are tools, you can do it with Nginx, HA proxy, or S-tunnel. You can just proxy pretty much any TCP traffic over TLS. There's a variant of TLS called DTLS for UDP. TLS itself won't run over UDP because it requires reliability, and it has to maintain messages have to be ordered. And then Quick also uses an implementation of TLS for connections over UDP. Let's go over some crypto quickly. This isn't a crypto talk, but I'll cover the basics quickly. Asymmetric cryptography relies on 2 keys, a key pair, a public key and a private key. Public keys are publicly distributed, and they're used to encrypt messages and validate signatures. And private keys are secret, and you're never supposed to share them. And they're used to... Oh, whoops, there's a typo. They're used to decrypt, and they're used to generate signatures, not validate, and not encrypt. Not every single asymmetric cryptographic algorithm will support both encryption and signatures. It depends on the algorithm. They're kind of slow and they're limited in message size, but the fact that you have a key that you can share with everyone makes them very useful for setting up a connection. There are several algorithms available for asymmetric cryptography. The ones that come up in TLS are RSA and ECDSA. Diffie-Hellman also is technically under asymmetric cryptography, but we'll cover that later. Symmetric cryptography relies on one shared key between everyone participating, and only trusted parties should have the key. It's not something you can share. Symmetric cryptography is really fast. Often there's hardware acceleration. There's block ciphers and stream ciphers. Block ciphers have a mode of operation, which is essentially how you encrypt data with multiple blocks, because block ciphers operate on a discrete size of message, whereas stream ciphers work on any size of message. Signatures, you can also do signatures with symmetric crypto, but you can't have a signature that anyone can validate. You either use an HMAC or use an AED cipher. And then there's several algorithms that come up in TLS, AES and CVC mode with an HMAC, AES CCM mode, and then AES GCM. And so AES is a block cipher, and then the other cipher that tends to be supported in TLS is ChaCha20. Poly 1305 is the it's used for maintaining integrity of messages. Key exchange. So there's various ways to exchange keys. So when you initiate a TLS connection, the the goal is to exchange establish a shared secret so that both sides, both the client and the server, can use a symmetric cipher. You can use RSA for exchanging keys, where you encrypt. Usually the client, I think, will generate a secret, encrypt it with the server's public key, and then send it to the server. And that way they both have the same secret. You can also use Diffie-Hellman to generate a shared key. Right, let's talk about the handshake. So basically, TLS operates on top of TCP. So you first have a TCP handshake, followed by TLS handshake, and after that, you can transmit application data encrypted.
Well, I have a question.
Yeah.
If I don't use RSA, if I use Diffie-Hellman instead, how do I know that? How do I prevent a man-in-the-middle attack?
So if you're in that case, I probably covered it at some point, but you you sign the parameters that you use for Diffie-Hellman using your certificate, using your public key, or using your private key, and then you verify it with the public key. So if you're only verifying server certificates, then what'll happen is when the server sends its Diffie-Hellman parameters, it'll sign it, and then you can validate that the server generated those parameters. Yeah, Diffie-Hellman without any signatures is vulnerable to man-in-the-middle attacks. TLS doesn't have that. Right, so the handshake starts with a TCP connection. That takes a round trip, and then TLS 1.2, there's 2 round trips. Basically, the client says hello, then the server says hello, sends over a certificate, and then the client sends some key information, and then the server does some, both sides compute the symmetric keys, and then the server sends back a message saying it's finished. In TLS 1.2, you can not use Diffie-Hellman, and you can also not use a cipher that has authentication built into it. That's not a good idea, but actually, so banks and certain network monitoring software sometimes will opt out of Diffie-Hellman so that if you're not using Diffie-Hellman and you have the certificate or the private key, you can decrypt all traffic from logs, which is not something you can do with Diffie-Hellman. In TLS 1.3, they made a bunch of improvements. So in TLS 1.2, you would have to choose a bunch of ciphers. TLS 1.3, all the ciphers are good. There are no ciphers that are completely broken. It still runs on top of TCP, but they cut down the key exchange to 1 round trip. Only authenticated ciphers are available, and you always use Diffie-Hellman for key exchange. That actually caused an issue for lots of monitoring tools. And there's also an option called 0RTT, 0 round trip time, where you create a new connection to the same server, and you don't have to go through any round trips by remembering some old crypto data. Actually, 0RTT has an issue where if you send the message again, you can like repeat it, and the server will keep on accepting it. And so if your application isn't built to withstand repeated messages, then you can run into security issues. So this is just the crypto in the handshake. The client says hi, the server sends a public key, the client generates a secret, encrypts it with the public key, and sends it to the server, and then both the client and the server have a shared secret. The problem with that is any conversation that's been logged can be decrypted in the future if the server's private key is ever leaked. So if you do a key exchange over Diffie-Hellman, then you can't work out what the shared secret is, even with the private key, because the private key isn't used for encrypting any data, it's just used for signing data. And it is important that you sign it, and TLS does. So we have this handshake, and the server can talk to the client, and the client can talk to the server. But how does the client know? So the server sends a public key to the client. How does the client know that the public key actually belongs to that server? This is the fundamental issue behind TLS. Once if you TLS provides all these guarantees on the assumption that you can trust the uh, server's public key, or you can trust that the public key that you get actually belongs to that server. How do you solve this? Well, one way of doing it is a key signing party where everybody goes up to each other and looks at each other's ID, and then you share keys using pencil and paper.
Wait,
Obviously,
how do you know their IDs are valid?
well, so the way key signing parties work is you just the problem that you're trying to solve is how do you associate a person's identity or a system's identity to their public key, because there's nothing about you that links you to a public key. So if somebody claims to have that public key, then and you can verify that it's actually them, then you know that they are giving you that public key. So essentially, you can trust that the public key belongs to them. If they provide someone else's public key, then you won't be able to talk to them because they won't have the private key. So there's like no point in doing that. So they'd provide their own public key, and there's no way for someone else to provide their own public key and pretend to be another person because you're verifying their identity, or so you're supposed to. I suppose if you were to fake an ID, it may be possible to do something at a key signing party, but typically that's hard to do with face-to-face. Obviously, computers can't do that. Not only does that require like human intervention, it's also slow. So computers do this via certificates. Certificates are just public keys attached to extra information. The extra information allows you to understand the identity of whoever is presenting the certificate. So the public key you can use to authenticate someone, that is to verify that their identity, to validate their identity, and then the certificate data will tell you what they can do and who they are, and based on who they are, you can figure out what they can do or what you will allow them to do. Now, you can't just have like data independent of the public key. So the way they're attached together is by putting them together and then signing it. And so now if anyone were to tamper with the extra data, then the signature wouldn't match. And then there's also a certificate authority that attests to the validity of the data, because if I can create a certificate saying anything. How do you know that it's really me? Well, a certificate authority attests to the validity of that data. X509 is the standard for certificates that pretty much everyone uses. It's used for email, it's used for TLS, it's used for other things, government IDs, I think. There's a lot of fields in the certificate. There's a full standard. You can add custom fields. This is not an exhaustive list, but in general, there's things like country, state, organization. Really, for websites, the only thing that really tends to matter is the common name, which is where the domain goes, the domain name of the website. So if you visit google.com, then the google.com will be in their common name. There's actually another field that I can't remember off the top of my head where they put that stuff. But you have to know which field to look at, and it's in the standards. And then there's other information like what you can do with the certificate. So key usage says you can do, like key usage will have different things set, like if you can use it for signatures or encryption or exchanging keys. And then extended key usage will also have more information about what you can do with the key, like if you can use it as a client or a server or both. Yeah. A certificate authority signs a certificate. So how do you know to trust the certificate authority? We've just pushed the problem back. You can sign the certificate authority with another certificate authority. But you just keep pushing the problem back. So eventually you need to establish a certificate authority that you trust. And that means you trust it to accurately issue certificates to other entities. The authority, the root authority is put in what's called a trust store. The trust stores are available in many different places. So Firefox has its own trust store. Windows has a trust store. Apple has a trust store. Android has a trust store. The trust store is just pretty much a list of certificates that it trusts. So because you can have certificate authorities assigning certificates for other certificate authorities, you essentially have a chain of certificates when you're validating, and that's called a certificate chain. Right, so this is about trust stores. So case study on, so the thing about trust stores is, the thing about trust stores is you have to trust what's in the trust store, and if that trust is violated, all of TLS breaks. Pretty much none of the guarantees hold. And one case where this happened was with Superfish was an advertising company, and they worked with Lenovo to bundle their certificates into the trust store of the Lenovo laptop. The software would intercept your browser traffic and then inject ads. And to do that, they had to decrypt it and then essentially run a man-in-the-middle attack. The problem is they use the same certificate on every single device, and because all the interception was happening locally, every device had the same private key. And so if you just had one of these devices, you could get the private key, and then you would essentially be a certificate authority that's trusted by all these other devices, which essentially allows you to intercept traffic for any website on a device that trusts that certificate. So moral of the story is, if your trust store is compromised, TLS's guarantees don't hold. So you just check that there's a chain of certificates, right? No. So let's say you've been issued a certificate, and then you create another certificate, and then you sign the certificate with the certificate that you're issued. So, I mean, how can you do that? When you get a certificate, it has the public key, and it is a certificate. So you could, and you also have a private key, and so you could sign another certificate with your certificate. So in theory, you could sign a certificate for Google.com. This is obviously not a valid chain. So how can you tell? In the X509 extensions, there's something called basic constraints, and one of them is a flag that says if you're a CA. So if you get a certificate for a website, the certificate authority is supposed to set that flag to false, that you are not supposed to issue certificates. And when you validate certificates, you have to check that the flag is true whenever you're looking at a certificate authority certificate. And there have been cases in the past where the validators didn't do that, which essentially breaks TLS. So don't do it yourself. Use an established library. Don't roll your own crypto. So you just do that. So if you check if it's a certificate authority and that it's a valid chain, you're good, right? No. You also need to check that the information in the certificate is valid. If you don't do that, then you just check that the ID is a valid ID, but not that the ID, the entity that is identifying themselves is actually allowed to do something. So what I mean by that is, if you go to like google.com and then you get a valid certificate for like ISSS.io, it could be a valid certificate, but that certificate is not valid for representing google.com. And if your browser doesn't check that, then you run into issues. Essentially, TLS breaks. And that sounds like an obvious thing to do, but that doesn't happen in a lot of cases, particularly for Wi-Fi authentication. Wi-Fi authentication uses certificates, and a lot of devices will just check that the certificate chain is valid, but not that the domain name matches anything. So you can get another certificate and pretend to be that Wi-Fi access point, and it completely breaks the guarantees of TLS. So how do you keep talking about getting certificates? How do you get a certificate? You have to get it issued by a certificate authority. Technically, you can make your own certificate authority, but unless anyone trusts that certificate authority, it won't be very useful. Enterprises will sometimes do that, and they will have all their devices trust their own internal certificate authority. Do not give the certificate authority your private key. You don't have to get a certificate. In fact, it's a bad idea. The private key doesn't leave your possession, and it shouldn't, and this is not an exception to that. The way you get a certificate is you create what's called a certificate signing request, and you say, for example, you want this domain, and you include other information, whatever the certificate authority wants, and then you sign it with your key, and you send it to the certificate authority. And if the certificate authority deems that you are authorized to get that identity, then it will issue a certificate. How does it check that? That depends on exactly what's happening. But for websites, there's an automated protocol called ACME. ACME version 2 is standardized. And Let's Encrypt uses this for providing free certificates. If you want something like an email certificate, you'll have to go through a different process. There's like various providers that are commercial. UT has email certificates for people at UT. And you have to go through whatever their process is to get the certificate. So if you have a certificate, what do you do if it's compromised? You have to revoke it. Well, you're supposed to revoke it. Browsers should check if a certificate is revoked, but revocation comes with many challenges. The way revocation works, well, one of the ways revocation works is when you ask the certificate authority to revoke your certificate, it'll add it to a list of revoked certificates in a list, and that list is called the certificate revocation list. If they issue a lot of certificates and a lot of certificates get revoked, it can be a pretty big list, and downloading that every time can be a problem. So you're not going to use CRLs for end entity certificates, but intermediate certificate authorities might use them because there's only going to be a few certificate authorities, so the list would be quite small. The other way of doing revocation is OCSP. You query the certificate authority and ask it if a certificate is valid. OCSP is short for Online Certificate Status Protocol. There's a privacy concern with this, which means every time you want to check if the certificate is valid, you have to ask the CA, which now tells the CA what certificate you're validating. So when it comes to websites, you'd be telling the CA what website you're visiting. It also puts a lot of load on the CA. If the CA issues, like 10 certificates, and then each of those 10 certificate users have like 1,000 people visiting their site, then you have like 10,000 people, 10,000 requests to validate certificates. So it puts a lot of load on the CA, and also the CA has to be online for the certificate check to work. So once the CA issues a certificate, it doesn't have to be online for verifying a certificate. But if you want to check if it's been revoked, then you have to contact the CA, and if the CA servers are down, then you can't check if it's revoked. So what do you do then? Well, if the check fails, the browser will say, oh, there's been a problem, it's been revoked. If the check times out, then the browser is going to typically just continue with the connection, because if the CA is down, then if you stop people from accessing the website, that presents a usability issue. But the problem with that is an attacker can just block requests to the certificate authority and make it seem like it's down, which will cause the browser to accept when in this case could be a revoked certificate. So certificate revocation is really broken. There is one last thing, but it's not super widespread and depends on browsers. Every now and then, you can have the server ask the certificate authority for proof that the certificate is still valid. So the certificate will expire in some amount of time, and this proof that the certificate is valid will typically last for a much shorter period of time. I think 7 days is what Let's Encrypt uses. And then you attach that proof to the certificate when you're talking to the client. The benefit of this is clients don't have to contact the CA, so it protects the privacy, it reduces load on the CA. The CA doesn't even have to be up because, once the server gets the proof, it can reuse that proof until it expires, and then it has to ask for another proof. And so that's good. The problem is if an attacker has hold of a revoked certificate, they can just not include the proof. So the way to fix that is by asking the certificate authority to put a flag in your certificate that mandates the browser check for the proof. And if it doesn't get that stapled OCSP response, it will reject the connection. Do browsers actually do this? Chrome doesn't. Firefox does. I'm not sure about the other ones. What happens if a CA misissues a certificate? Yeah, it's pretty bad. But there are attempts to make the problem less bad. One of them is certificate transparency. So certificates that are issued for websites are logged in public append-only logs, and people can publicly audit them, and they're not supposed to change. Anything added to the log. So you can only add more certificates to the log, and it becomes this massive list of issued certificates. I think Chrome and probably Firefox too, at this point, they reject certificates that are not in logs. So when you get a certificate, it actually includes a proof that was added to a log. And if it doesn't have that, then the browser will reject the certificate. So this essentially forces authorities to add certificates to these public logs. And by doing that, you can watch for misissued certificates. If you're watching logs for your domain name and you suddenly see a certificate get issued that you didn't, you can be alerted to a misissuance. The other thing you can do is you can also add a record in your DNS records called a CAA record. Certificate authorities are supposed to check these CAA records, and essentially the record lists certificate authorities that are not allowed to, or it does a whitelist. It lists certificate authorities that are allowed to issue certificates for your domain, and any authority that complies with the browser and CA forum rules should be checking these records, and if they're not on that list, then they will not issue the certificate, in theory. So what happens if your identity changes? Surely the certificate authority needs to revalidate your identity every now and then. And yeah, so certificates are only valid between 2 dates. So there's a date before which the certificate is invalid and a date after which the certificate is invalid. But the problem with that is you have to be able to, when you're validating it, you have to know what the time is, which sounds like a simple problem, but in reality, managing time is a problem for computers. NTP is the age-old solution for that, a network time protocol, where you get your time from over the network. NTP is not authenticated. They have some authenticated modes. Most people don't really use them. There's newer authenticated stuff that's in that are in protocol drafts, but reality, NTP isn't authenticated, and it is a potential attack vector where you If you have an expired certificate, you could potentially use it by tricking the computer into thinking that the time is different. However, browsers are aware of this. So something like Chrome, if your system clock, so Chrome will check against what they trust to be a reliable source of time, probably some Google server, and it has its own authenticated protocol for getting that time. So if it detects that your system time is significantly different from what it expects, then it'll actually reject connections and alert you that your system time clock is skewed. Let's talk about key generation. There's an assumption about that you generated keys properly, which doesn't always hold. If you don't have enough entropy in your system when you're generating RSA keys and your software isn't designed properly, then you can potentially generate weak keys. What do I mean by weak keys? You don't have enough randomness to generate keys. So over a large number of people generating keys, your keys might share some common factors with somebody else's keys, and that makes that kind of breaks the security of RSA or whatever asymmetric cryptographic scheme that you're using. I think this paper looks at RSA in particular. So when you're generating keys, this is an often overlooked area. You have to be wary of how you do that as well. Right. So you might think that after all of this, even if you account for all of that, when you connect through HTTPS, then more or less things should be fine. And I guess that's the case. But typically, when you go to a website, how often are you really checking that it's over HTTP or HTTPS and not over HTTP? Because you might just assume that you get redirected, and that is the standard practice for browsers to, or for websites to redirect you to HTTPS. But they still support an HTTP connection. Usually that HTTP connection redirects you to HTTPS. But if your browser makes the initial connection over HTTP, which it often does, an attacker can intercept that connection and run a man-in-the-middle attack where they establish an HTTPS connection with the server, but between you and the attacker, there's an HTTP connection. And that can be done with the SSL strip tool. And essentially, it removes the layer of TLS by making it seem like you have an HTTP connection to something that shouldn't work, because the attacker is relaying all your traffic. And the only way to not do that is to not make the initial connection over HTTP. There's actually an extension by the EEF for doing that. It's called HTTPS Everywhere, I think. Yeah. But there's also mitigations in the HTTP protocol for that. Yeah, the EFF is awesome. They have some pretty neat extensions. So HSTS is a header. It's for HTTP strict transport security. I think that's what it stands for. The HSTS header, when you connect to a website and you get back an HSTS header, that tells the client to only use HTTPS for all the subsequent connections. So whenever you connect the first time, again, your initial connection will be over HTTPS. In fact, we had that issue with our CTF setup because our CTF problems, our web problems, don't run over HTTPS, and we accidentally put an HSTS header in our ISSS web page or something, or the main CTFD web page, and everybody's connections were getting defaulting to HTTPS. And once you see an HSTS header, browsers will try pretty aggressively to not go back to HTTP. So the warning that you get when you have a bad TLS connection, the browsers actually get rid of the option to fall back to HTTP if the HSTS header was present on that site. This still doesn't cover the very first connection though, because the very first connection could be over HTTP. And the way to fix that is to just add your website to a list that I think Google maintains, and browsers will literally hard code your domain into their source code, so that when you make when someone visits your website, the first connection will be over HTTPS. Is there more? Yeah, there's a lot, but I can only talk for so long. I'm going to leave you with this tool, sslabs.com. It can test your browser, but most people's browsers, as long as they're updated, is fine. This is really useful for testing TLS configurations on servers. It'll run a suite of tests and check for vulnerabilities, and give a nicely formatted report for what you're doing wrong and what you're doing right, and what changes you can make. And that's the talk.